Hey, chemistry students, this is Ms. Ruark. This is podcast 6.3, where we're going to take this stoichiometry stuff just a little bit further, and we're going to talk about what happens when um, when you don't know which one of your reactants is in excess. Okay, and so we have to figure out our limiting reagent. All right, so caution. This stuff is difficult to follow at first, but it's not impossible. Just be patient with me, make sure that you're paying attention, and ask lots of questions. Okay? Pause this, rewind it, watch it again if you need to. Just pay attention. Okay, so stoichiometry is like a recipe. It's like cooking. Okay, so let's say that we are going to make a cake. And to make this cake, we need 2 cups of flour, 2 eggs, 1 cup of sugar, 1.5 tablespoons of baking powder, a cup of water, and 1/3 of a cup of oil. All right, you go look in your kitchen and you see that you have 14 cups of flour, you have 4 eggs, you have 9 cups of sugar, 15 tablespoons of baking powder, 10 cups of water, and 3 1/3 cups of oil. And we want to know, how many cakes can we make? Okay, how many cakes can we make out of that? All right, so if we have the flour, we need 2 cups, but we have 14 cups, so we could make a total of 7 cakes. With the eggs, we need 2 eggs. We only have 4, so we can make a total of 2 cakes. With our sugar, we need 1. We have 9, so we can make 9 cakes. With our baking powder, we need 1.5. We have 15, so we can make 10. With the water, we need 1. We have 10. We can make 10. And with the oil, we need 1/3 of a cup. We have 3 1/3, so we can make 11 cakes. All right, so the question is, how many cakes can we make out of this? Right? So how many cakes can we make? Well, if you look at it, let's go back and look here. Oh, go back. Here we go. We can make 7, 2, 9, 10, 10, and 11, right? But if we make this 11 here, it's going to be kind of gross because it's only going to have oil in it, right? So we have to go with what limits us from making more than a complete and total product. So how many total baked cakes can we make? Well, we can make 2 cakes. And the question is why? Well, because everything else runs out. Okay? Or this runs out and everything else is still there. And if you make a cake without eggs, it's not a cake. It's really kind of gross, right? So only 4 eggs. We have extra of all the other ingredients. The eggs is what we call our limiting reactant. It limits us from making more product. All right, so how does that work in chemistry? Well, we have limiting reactants in chemistry. They limit us from running the reaction further. Okay, so if we have, and I know this isn't written down, but you'll need to write it down anyways. So let's say we have 4 ammonias, and we're reacting 5 oxygens with that. It will produce 6 waters and 4 nitrogen monoxides. All right, so how many moles of nitrogen monoxide are produced if blank moles of NH3 are burned in blank moles of O2? So we have 4 moles of NH3 and 5 moles of O2. Well, look, we need 4 moles and we need 5 moles. So if we react 4 moles of NH3, we can make 4 moles of NO. How do we know that? Well, 4 moles of NH3, and I'll write it out on this first one. I'm not going to do it on all of them. All right, and we know that our mole ratio of NH3 to NOs is a 4:4 ratio. 4 times 4 is 16, divided by 4 is 4, so we can make 4 nitrogen monoxide. Okay, well, what about the moles of oxygen? Well, if we have 5 moles of oxygen, our mole ratio of oxygen to nitrogen monoxide, NO, is a 4:5. Okay, those will cancel and we end up with 4. So we can make 4 nitrogen monoxides with both of these amounts. All right, what if we have 4 moles of ammonia? We know that this will give us 4 moles of NO. What if we have 20 moles of O2? Well, if we have 20 moles of O2, we know that our ratio here is a 4 moles of nitrogen monoxide to 5 moles of O2. Right? So 20 times 4 gives us 80, right? And then 80, what's 80 divided by 5? 80 divided by 5 is 16. So this tells us we can make 16 moles of NO. But this one says, nope, you can't. You can only make 4. All right, well, what if we have 8 moles of NH3 and 20 moles of O2? Well, we know with this one we can make 16 moles of NO. If we have 8 moles of NH3, we double this, so we can double that, and we would make 8 moles of NO from this one. I can't write right now, sorry. All right, so the total we can make is 8. Okay, hopefully you're following along with me. If not, don't worry about it. It'll make sense. Let's keep going. All right, so here's another example. I think I skipped an example, did I? Yes, it's gone. Okay, so the question here is how many grams of NO are produced if 4 moles of NH3 are burned and 20 moles of O2? All right, well, if we go back and look, we have 4 moles and 20 moles. We said the most that we can make is 4 moles of nitrogen monoxide, right? Because NH3 is our limiting reagent. We have to use this as our given quantity in the calculation. We kind of just ignore this for now. We might need it to come back, but we're just going to kind of ignore it for right now. All right, so we know that we have 4 moles of NH3, and we said we can make, in the previous problem, 4 moles of NO from there, and then all we have to do is do our conversion to go from moles to grams of NO, and moles cancel, and then that would be 120.04. Yep. Okay. So we have to figure out which one runs out first. Okay, so the question is, well, how do you know which one runs out first? Okay, well, I'm going to show you a couple different ways to do this. All right, so we've got the same equation, and it says how many grams of nitrogen monoxide, so we're looking for grams of nitrogen monoxide, are produced if we have 20 grams of NH3 and 30 grams of O2. So the first thing we need to do is find the grams, or find the moles of each one. So if we start with 20 grams of NH3, okay, we know that 1 mole of NH3 is equal to 17.04 grams of NH3. And when we do the math on that, we get 1.174 moles of NH3. I'm not going to keep a whole bunch of numbers. I'm just going to keep some. All right, and then 30 grams of O2. We know that 1 mole of O2 is equal to 32.00 grams of O2. Okay, when we do the math, we get 0.9375 moles of O2. Okay, so remember, whenever in doubt, you always go to moles, right? Because you can compare moles to moles here. Okay, so now we're going to use a comparison chart to compare our moles. All right, so we have and we need. Okay, have versus need. So let's look at these. All right, NH3. We have, we said on the previous screen, 1.174 moles, and we need 4 completely. Okay, and with O2, we have 0.9375 moles, but we need 5 moles. Okay, so notice how we need more of the oxygen than we do of the ammonia in order to make 4 moles. I'm not even going to write that there. In order to make 4 moles of the NO, we need 4 and we need 5, but we only have this amount here. So the question is, how much are we going to make? Well, if you'll notice, we need more of this than we do of that. So this is actually the one that's going to run out first. Well, how do we know? Well, because we look here at our mole ratio, and our mole ratio tells us we need more, but we don't have more. So this is going to be our limiting reactant. All right, so from this chart here, you're going to perform the stoichiometry using the limiting reactant as the given quantity, meaning what you normally get in the problem. Okay, so how does that work? Oop, go back, sorry. So we're going to take that, we can just start from here, 0.9375 moles of O2, because we know that's the same thing as the mass, or you can start with 30 grams of O2. It doesn't matter, you'll still get to the same place. All right, and we're going to go until we get to grams of NO. Well, we've got moles of O2, we put that here, and moles of NO. Okay, and if you look at your balanced chemical equation, 5 O2s and 4 NOs. So we're going to plug that in, 5 O2s and 4 NOs, but we want grams. So we're going to do moles of NO on bottom so it cancels, and we know that that is 30.01 grams of NO goes on top. Okay, these are all canceling. we're left with grams of NO. That's what we want. Okay, so when we do the math, it tells us that we get 22.5075. We don't want all that. We need, it started out with 30 grams. How many significant figures? One significant figure. So we would round that to 20 grams of NO. Okay, and that's what you do. And then the NH3 would be what we say in excess. There's too much of it. There's more than enough. Okay, now you can do it that way where you're comparing. And if you want to, great, go for it. But then you can also do what I like to call the shortcut because you're not having to do a comparison. It's up to you. Okay, so you do two separate calculations using both given quantities, and then the smallest answer is the correct answer. Okay, so we've already done 30 grams of O2, and we said if with 30 grams of O2 you can get 20 grams of NO. Okay, we've done that before, so I'm not going to go through it again. But we don't know with 20 grams of NH3 what we would get. So 20 grams of NH3, and you do the whole stoichiometry, just like we did with this one before. So we put 17.04 grams of NH3 on bottom, 1 mole of NH3 on top, and then we do our mole ratio of moles of NH3 to moles of NO. Okay, it's a 4 to 4 ratio, so we put a 4 and a 4. NH3s go away, and then we've got 1 mole of NO is equal to 30.01 grams of NO. Okay, and then we do our math. So when we plug this all into the calculator, it gives us something like 35.223, yada, yada, yada. We don't need all that. We just need one significant figure, so it's going to be 40 grams of NO. Okay, so which one's smaller? This one. So this would be our final answer, and this is what we would call our limiting reactant. And so we're able to tell not only our limiting reactant, but how much we would actually make all in one step. Right? And it does the same thing. It just depends on which way you want to do it. Okay, here's a practice problem for you. I want you to actually practice this using that shortcut method, and I want you to check your answers with me when you come into class tomorrow. Actually, this is one of the ones I'll be looking for when you come in tomorrow, so make sure you have it. Okay, yield. Let's talk about this real quick. Yield is the amount of product that's made in a chemical reaction. There are three types of yields. Okay, there's what we call an actual yield, and that's what you actually get in the lab. It's what's measured, it's what's produced. Okay, those are some words that you'll see to go with it. The theoretical yield is what the balance equation tells you you should make. Okay, that's what we've been calculating this whole time. This is what we have been doing this whole time. This one we have not, because that's what you would measure after you do your lab procedures. Okay, and then you have your percent yield, and your percent yield just it is a percentage of what you made, and it tells us well, that's on the next slide. It tells us the percent that you made, percent made, as opposed to what you should have made. So it tells us how good your reaction it is, and the closer to 100 it is, the better. Okay, it's a better reaction if it's closer to 100. Okay, so percent yield tells us how good a reaction it is. Okay, percent yield should not be more than 100%, but it can be if you do something wrong, you get your sample's contaminated. Okay, theoretical yield's always going to be larger than the actual yield, and the reason for that is because of impure reactants. You've got side reactions going on, you lose product in filtering, transferring between containers, tons of reasons why. So just know that your theoretical yield will always be larger than your actual yield. And to calculate percent yield, we do actual yield over theoretical yield times 100, and it gives us our percent yield. All right, so here we have 6.78 grams of copper is produced when 3.92 grams of aluminum are reacted with excess copper. So we've got aluminum and excess copper 2 sulfate, and it's a single replacement reaction. So we have Al2SO43 plus Cu, and then we balance it. This gives us 2, this gives us 3, and this gives us 3. Okay, now I'm going to run out of time, but I want you guys to try something. This right here tells us it's produced, so it's going to be 6.78 grams of copper. Okay, to get our theoretical yield, to get this, we have to do our stoichiometry. 3.92 grams of aluminum how many grams of copper. And then for the percent yield, actual over theoretical times 100. So I want you to finish this up and try it. And I want you to do this one. And those are the ones I'm looking for when you come to class tomorrow. See you then.